Hello, everyone. Good evening, good afternoon, good morning. We are here today to another session of our webinar of our event, which is the 7th Geoscience Remote Sensing Young Professionals, and also the IS-PRS Student Consortium Summer School. Before we start our lecture, I will give a little bit some announcements about the session, and just a moment here. Our event was being organized by Geoscience and Remote Sensing Brazilian chapter. In this event this year, we have a lot of webinars, roundtables, tutorials, and it was organized by UDESC, University of the State of Santa Catarina, and the Community University, UNO Chapecó. We have the support of Geoscience Remote Sensing Society through the Young Professionals, and also from the International Society for Photogrammetry and Remote Sensing, and which is represented by the Student Consortium. Please access our website for the event. We have it is a free registration for the conference. We have a lot of activities this year. We have the support from FAPESC. It's the funding agents from Santa Catarina State, and also from two companies, Canoinhas, and also the Instituto Gilson Von Pato de Educação Científica. We have support also from other universities from Brazil, INPE, PUC-Rio, University from Paraná, UNOeste, UFMG, UFMS, and also UNESP. We had already some talks given in our event, and you can check it out in the YouTube channels of the Brazilian chapter of IEEE Geoscience Remote Sensing Society, and also in the ISPR Student Consortium channel in YouTube, at YouTube. So today we will have a talk by Professor Devis Tuia from EPFL, Switzerland, entitled Change Detection in the Era of Deep Learning. So I would like to invite Professor Devis Tuia. Hello, Davis.
Hello.
It's a pleasure to hear your talk. Professor Devis, it's a very important researcher in the geoscience and remote sensing community. He research. He have a lot of work, very important work actually, in the computer vision, machine learning concerning remote sensing stuff and tests. So it's a pleasure to have you here with us, okay? And the room is yours from now, okay? Thank you very much.
Thank you, Jefferson. Thank you so much.
You can share your slides, please.
Yes, I'll do that in a second. So good morning, good afternoon, good evening, everybody, wherever you are. So I'm in Switzerland. As you can see, it's still the day, so it's a beautiful day here in Sion. And
I'm sorry, your slides are not available at this moment.
The what?
May you can share, please?
Yeah. I just wanted to introduce before sharing. If you prefer, I can share the screen.
Yeah. Okay. I'm sorry. Go ahead, please.
There we go. Here is the screen coming. Hopefully. Okay, good. So let me also put this full screen. Can you confirm that you see the slides correctly?
It's
Jefferson?
okay.
Yeah,
It
full
works
screen, all
very well.
good. Excellent, excellent. So yeah,
Yes.
as I was saying, welcome everybody, wherever you are, if it's the morning or the evening for you. And so thanks for everybody for coming. Thanks to GRSS Brazil chapter for having me. Also the the SPRS Students Consortium. We already met last year. I gave a talk about wildlife there. So today is going to be a little bit different. So at least you don't get the same talk twice. That's good. And yes. So I'm Devis. I'm from EPFL, École Polytechnique Fédérale de Lausanne in Switzerland. And here I am the head of the Environmental Computational Science and Earth Observation Lab. And today I will talk with you about change detection. So that's a topic that has been pretty close to my heart for a while. And yeah, we will talk about how change detection has been going on recently, especially in what I called in the title the era of deep learning. So meaning that all this deep learning technology that you might have been confronted with or not. And if you haven't, I hope that you will, go home from this talk with some inspiration and ideas. Let's see, let's hope. So change detection. For those who have never been confronted to change detection itself, I would like to start like making sure that you realize that you already have been confronted to change detection. So you might be thinking, okay, what is this image? And this is basically what change detection is about. So you have two images of the same place, in our case of the same scene, and someone tells you that there are some differences between these two scenes. So I hope you're spending a little bit of the time that you are listening to me looking at these two pictures and start comparing. And the beautiful, incredible image processing software or hardware actually you have in your brain is actually doing an incredible job at the moment to try to find the difference. And this is usually the moment I ask people to unmute or raise your hand and tell me where the changes are. Well, I mean, we are in this virtual settings, which makes things a little bit difficult. But if someone who can unmute would like to play the game, Jefferson, if you want to give it a try, if you see a change, that would be awesome to see that your incredible brain that we all have works fantastically and allows you to find the changes. So to be honest, there is a bunch of them in between these two images. And I don't want to take 7 hours to do that, but I mean, if you want to really know where they are, I thought it would be nice to basically show you where they were. And there were 7 changes in between these two images. But I mean, despite the joke, which is always a good start for a talk, you can also see that the changes are very often very subtle. There are changes that are not easy to spot, and most of the things in the image actually often do not change. Sorry, there's a plane landing very, very close if you heard the noise. Okay, so I mean, in the remote sensing realm, I mean, the story is not so different from the 7 differences games we just discussed. Okay, we have quite a similar problem. So we have changes that are in principle quite rare with respect to the size of the image. We have changes that are small in size, and also that most of the image actually has not changed, right? But if this is true, that most of the image has not changed at all, like in the example of the beach and the animals and the ice creams, well, it could be pretty straightforward to actually detect all the changes in the images. And this, let's say, these were the first methods that were used to perform change detection. So like you take your 2 images, you subtract them one from each other, you have a difference vector. So you can do that in the magnitude domain. You can do that in the polar domain by looking at magnitude and angle, and then you will take everything that gives you a very small magnitude. So 2 pixels that are the same in terms of spectra are 2 pixels where nothing has changed. And when there was a change, so in, let's say, this area here on the graph, well, this is where all your changes should sit. Okay, so everything that is close to the origin is now changed. And when you move away from the center, then you will like to see your changes. So if this is true, then you can just put a threshold in. You can use Otsu method or your favorite one, and you will be able basically to detect it all. Okay, so this is one of the early methods for change detection, very successful. It's called change vector analysis, and it's something that's been applied several times to remote sensing images. If we just make an example from a project of my students back in the day, they took these 2 images in Colorado. There was a flood in the middle, and I mean, if you look at the 2 images, you can actually see the flood pretty clearly. But okay, if you apply the CVA as it is, so calculating the magnitude of the difference, threshold in it, and so forth, well, you get to a result that is fine. Like you detect the change, okay, but I mean, it will detect mostly the big changes, but it will also detect a lot of false positives, and we will see why in a second. Also, I mean, we will have to like play a lot of tricks to filter out all the small spurious changes. So a lot of post-processing is necessary for in the end getting to a change map that is usable for your monitoring tasks. So just imagine you want to send a team on the ground to check if people are in distress where it's flooded. Well, you don't want to have a million areas to visit, but you want to focus on areas where the flood is definitely there. Okay, so why do we have all these false positives? I mean, why is it more difficult than we thought? It's because what I told you before is not exactly true. It's not that most of the images not change, but most of the images actually change because Earth is dynamic, and when time goes by, well, things happen that are not related to the change of interest. So, for example, if you think of seasonal effects, well, you have, grass is growing. You have all kinds of seasonal effects that will make that your image, even if it's looking at the exact same place, maybe 1 month before, will give you spectral differences where there is no change at all. So take this example here. So this is a forest fire in Bastrop, and so this is an image acquired by Landsat before the event. And this is an image acquired by the same sensor after the event, and I highlighted in blue the area that was burned. Okay, so the blue line has nothing to do with the image itself. It's just the burn scar you want to detect. So even though you can see it clearly on different images of different sensors, and even after a few months, you see that, for example, all the vegetation reflectance here has changed a lot among the different points in time, and you don't want to detect these phenological differences in your change detector, because you are not after changes in vegetation, but you are after the actual forest fire. A second thing that very often plays tricks to change detection algorithms and image classification in general is that image illumination effects are sometimes very tricky to handle when you want to port models across acquisitions. And in the case of change detection, this is compulsory because you want to compare before and another image taken after the event. So unless the 2 images are acquired exactly at the same time, that they have the same clouds regime, and it will be very, very likely that your images will look very different. And if you don't believe me, I just made a little exercise. It was a few years ago. I was having my very happy postdoc time in Valencia with Professor Kamsvals, and I was renting an apartment in the center of Valencia, and this is like the window view from my apartment. And I just started to take some picture with my DSLR at different times of the day. And of course, I mean, you see just visually that these images look at the same object, exactly the same, because we are talking about 3 hours apart, but the images look completely different. And if you analyze the spectrum of the images themselves, so you have 4 o'clock, 5 o'clock, 6 o'clock, and 7 o'clock, well, you will see that your sky will start to turn reddish. So at the beginning, it's more of a blue, and then it goes reddish because we are going towards the end of the day. The buildings are at the beginning very bright, and then they start to become bimodal because part of the building gets covered by shadow and parts are not. And at the end of the day, everything is under shadow. And in the vegetation, we have the same. Like at the beginning, it's very green, and little by little, it starts to become black because the trees go under the shadow. So you see, images, visual properties change a lot between acquisitions, and this is something you need to account for. Otherwise, you will be ending up detecting changes just because an image was taken at another time of the day, or because it's a different sensor and the band's nanometric specifics are different, and things like that. Good. So the question is, what can we do to fight this and have some good change detection? And I would like to show you two things. So the first one will be like a bit of a brute forcing approach, where we will use basically a supervised method with a lot of labels in order to detect the changes, and hoping that the model will be high capacity enough to contain it all. And the second one would be to try to discount for this atmospheric illumination sensor effect that are bothering us a little bit in order to make the image space more similar. And when it's more similar, we can then consider all images as equal. And these are like the two parts of this talk that and I will try to give you an overview of every one of these two directions, starting by the supervised methods. So when I say supervised methods, I refer to machine learning algorithms that learn from data. And these are algorithms that need as an input image data, but they also need some annotations, some labels in order to train. So you need to know, for example, that some pixels are buildings, some pixels are trees, and you learn a model recognizing these objects, and then you will use this to detect your changes. So there is a bunch of those algorithms around. It's a field that is very healthy, and it has been going on for, I don't know, 40, 50 years in remote sensing at least. And so you have methods, for example, that are what we call nowadays traditional machine learning based. It could be your favorite one. It could be a maximum likelihood. It could be a random forest or a support vector machine, like in the case of this paper I want to show you. And basically, the thing that happens is that you have your two images. So I hope you can see my mouse. So here on the left, you have X1 and X2. These two guys are two images. You will extract some features, some information from the images. It can be the band values, or it can be some kind of texture. It can be mathematical morphology, you name it. There's a lot you can do, and DVI, vegetation indices. But at the end of the day, you create kind of a big matrix, each one corresponding to one image. You stack them, meaning that you put the two matrices together, because you assume that your two images are like same resolution, same location, and very well co-registered. And then you learn the changes using your favorite algorithm. In this case, it's a support vector machine, and this will give you what we call a change map. So that's one possibility. A second one would be to take your two images that you like before, extract the same feature for the two, and then make one cube minus the other. Okay, so for each slice of your matrix, so for each band, if you want, you will have a difference. So you will have a result in different tensors that you will then use to predict your change map using the method of your liking. Can be, again, random forest, maximum likelihood, you name it. So you see, these are two different approaches. On the left, you have something where you're basically keeping all the information together, and from that information, you detect changes. So since you have all the information, you can really extract changes of different type. And in the one on the right here, the difference image analysis, since you make a big difference, everything that will not have changed will have a value close to 0. And in this case, it means that you will not be able to distinguish things that have not changed. So basically, you will have one class of no change, and then you will have your classes of change you want to detect. So let me show you a couple of results. This is a tiny little subset of the images we were considering. And so you can see this is the image at time 1, so before changes occurred, and this is the image at time 2, so after the fact. So you can see there are some buildings here that have been built in between. And what happens is that when you use the DMC, you can really make all the difference clear, and you can see like, oh, this was a building and it's still a building. This was a grassland and it's still a grassland. But here is a soil that became a building. So you can really have a complete map of everything that has happened in the scene, because you're keeping all the original information and you give it to the classifier. In the case of the difference image analysis, DIA, you are not able to distinguish non-changed areas anymore, because everything that has not changed since you're making a difference goes back to 0. So basically, you see, everything that has not changed is close to white, which is the class that we attribute to the no change. So what is the column of the right here? So here on the left, we're using only the image bands for training the classifiers. And here on the right, we're using a lot of texture information. So texture, mathematical morphology, all kinds of indices in order to train our classifier. And thanks to the spatial smoothing and the context information you give when you extract textural features, well, you see that your final map is less of a salt and pepperish. It doesn't solve everything, let's be clear about it, but it's really a good step in the right direction. Okay, I've been 15 minutes in the talk and I still haven't said the words deep learning. So I suppose that people will start to become a little bit anxious that, it was in the title, deep learning, why is he talking about support vector machines? Okay, so let's move on and let's try to see things that have happened recently to port this idea of extracting features onto images and learning joint classifiers as a deep learning algorithm. And I would like to, show you a couple of results from a paper I like a lot, which is the paper by Rodrigo Daut and colleagues that basically translate something quite similar to what I just shown you into a deep learning setting. So I think that's actually a great work. And for those who have never worked or seen deep learning algorithms before, let me give you a 30-second, maybe 1 minute crash course on deep nets, so you know more or less what's going on. So a deep learning algorithm is an algorithm that will scan your image with a number of filters. So if this is your original image, the algorithm will learn these little filters here. So in this case, these are directional gradients or color smoothing filters that will scan your image as a convolution filter in image processing will do, and will basically give you filtered version of your original image. And then it will, in cascade, learn new filters that will work on these filtered images to extract even more high-level information. And by playing a game of learning filters and decreasing resolution of your filter space, it will basically be able to zoom out of the tiny little detail the original filter is looking at and trying to see some context, and then more context and more context. And hopefully it will learn things that are useful to solving the task. So in this case, the task is to tell me which brand of a car that is. So at the beginning, you will learn very small directional filters that will basically, show you where the car is more or less, and which are the very edges you have in the car. And then the more you get deep into the network, you will start to see doors and wheels, and then oriented views of the car. And with that information here, so filters that activate on this specific parts of the car, you will be able to predict that this is an Audi. So remember, in the first layers of CNN, you have things that are very small and geometrical, like oriented gradients and local features. And since the deeper you go, the more you zoom out, you will have very class-specific features at the very end. So for us remote sensors, this boils down to have an image as an input, and to learn a representation in the middle, so all these filters I was talking about, and then to use this representation to scale it back up and to have the final response. So in the next figures I will show you, you will often see a structure like that, which is you have an image, you learn your filter, and every time you downsample, then you get to a representation that it's often just one vector or a very small dimensional in the spatial domain activation map with a lot of features. And then you will use this representation and scale that back up in order to have a pixel response. Okay, so what did our dear colleagues at Onera in France do for applying this logic to change detection? So basically, they used a structure of two mirrored networks, so that you can see here in green. And you see, it's exactly the same structure I showed you before. You have an image, it goes in, it learns a representation, and then when the representation is informative enough, it uses it, like it decompresses it to the original image resolution to have a land cover map. And they use the same model for the before event and after event part, and then they combine these two maps in order to have the change detection map. So this is the first strategy they have. At the same time, they also try to, like in the difference image analysis, to take the two images into a single model and predict directly the change without going through the single uncover maps. So you see, this looks a little bit like the two things I showed you before with the support vector machines. And then they also go further on this logic, and they use like intermediary networks that will try to predict a binary mask and then use this binary mask to have a better solution, then to share filters, and they end up making it way more complicated. I mean, for a reason, because it works better. But it's often a variation on this idea of using one network per image input and then try to make some kind of late fusion. So in their paper, they basically show interesting results where they have an accuracy that looks pretty high. So we're talking about, in change detection, a 98% accuracy, which, it can seem extremely high as a number. At the same time, remember that change is rare. So you should use a metric that is like balanced towards smaller classes. So for example, a kappa statistic can be a little bit more informative in this case. And you can see that very quickly the statistics go down extremely because it's difficult to detect changes. And every time you miss a change, this number go down. While, I mean, if you use it accuracy, if you were not predicting any change at all, you will probably already achieve a pretty high score. But okay, we're talking about 25% accuracy. That might seem very low to some of you, but don't be fooled by the numbers. So just don't be fooled by them. I mean, if you look at other methods for change detection that were proposed in the literature, I mean, you see that they are not even a 1% kappa statistic. So the problem is extremely tough. So it's a problem that requires advanced algorithm and is far from being solved. And this is a good news for many of you, because I mean, it's still time to jump in the change detection wagon with deep learning because it's far from being solved. And you can see, for example, in the results here, when you simply take strategy one and you take, so let's go back. So this strategy where you predict the two maps and you try to combine them, well, your results will be very dependent on the quality of the original maps. So you see this prediction compared with what you should achieve is not very good. But this is because the land cover prediction for the first image is actually very bad. So you're basically propagating errors because you are making late fusion of maps that are not very accurate. While you have a system that is integrated, well, you start to really get close to the change that you want to detect, like you see here in the example of 4.2. So how can we do better? Doing better, well, I think one key aspect of doing better in this case is related to having more data, more annotated data that have more diversity, more samples, and also having more geographical diversity. Because of course, as long as you train and predict in the same type of geography, everything works fine. But if you start to train models all over the world and predicting in other areas of the world, then your model is more or less doomed to fail, because it has never seen this type of color combination, this type of spectra. So it's a very, very complicated task for a model like that to actually be able to detect the changes properly. The good news for all of us is that, you know, the things are starting to happen. So there are data sets, for example, SpaceNet 7, where they give you data on different places of the world, where you have time series, where hand labels with like all the buildings appearing, and little by little, you know, we're creating a database that can be used for effective change detection. But you see, I mean, the SpaceNet 7 was last year, and if you look at the performance of the winners, we're still around 40% accuracy. So again, the problem is far from being solved, and for sure, it cannot be solved just by bombasting some computer vision architectures, like you can see here in many of the winners' propositions. It's like a combination and ensembling of many neural networks. And I think that we need to go further than that. And we cannot just consider that we can solve everything with, you know, with a cascade of ResNets or things like that. And this is actually what brings me to the second part of the talk. So I hope you're still alive and enjoying the ride. I'm actually enjoying it quite a lot. And so I wanted to take a first step in the direction of doing something that is maybe a little bit more thoughtful of the problem at hand that we are considering. And in this case, I would like to discuss how we can make image spaces more similar, and then use what we call a self-supervised model. So the idea, it's pretty simple. You want to take your images and you want to modify their spectral information. So you want to modify their color, if you want, in a way that all the parts that are not changes look much more similar than they used to be. And by doing that, it will forcibly highlight the changes much more. So if you take the example of before of our forest fires, we will like that all these, you know, parts that are green here are also green here, because these are changes that we do not want to detect. So we would like to align the data spaces so that everything that we know isn't changed gets the same values. So of course, it's really an image processing reflection. I mean, I don't want to create an image where the vegetation changes color. I want to work in a space that is good for change detection. And this is something we studied a few years back with Michele Volpi, and we looked at projective methods. And one that we really enjoyed using was called the kernel canonical correlation analysis. And it was basically a kind of a multidimensional projection that will try to align data spaces to each other. So we were highlighting with a scribble, just with a line on the images, regions that we knew were not changed. So this is like an interaction that takes 10 seconds. And then the algorithm, by using these pixels that are supposed to be unchanged in the two images, will take the respective data spaces and trying to align them as much as possible by maximizing their correlation. So, I mean, you could see that a little bit as a nonlinear principal component analysis that looks at the two spaces together and try to maximize their correlation in areas that have not changed. The cool thing is that since you're now trying to align data spaces in a kernel space, basically you can align different sensors because it becomes completely independent of dimensionality. And this is very cool because it allows you really to make change detection across sensors. This is something that, for example, CVA cannot do because you need to first calculate the difference between two images. And if the two images have different bands, then you're done. So it worked okay back in the day. I mean, of course, it was a first try. But you can see here, every line is one experiment. So in the first line, we're having two same images from the two same sensors. So we have Landsat 5 before the fire and Landsat 5 after the fire. And after alignment, the two images look like that. And after they are aligned, the two spaces are of the same dimensionality because they have been aligned. Well, okay, they were of the same dimensionality before as well. But you can then do one minus the other and get a difference image. And in this different space, then you can apply the CVA, and having your thresholding, they will highlight the change pretty neatly. Now, if you start to use different sensors, so we have Landsat 5 before the event versus Ali after the event, we have a sensor that has 7 bands versus a sensor that has 9 bands. So you basically cannot compute the difference. But here, by using this projective method, we are basically projecting into the common space of same dimensionality, where we can play the exact same trick and making a difference and having a detection. But as you can see, the two spaces, the original spaces are of different dimensionality. So the projection is not perfect. So this is why you start to see more artifacts that, of course, you will have to post-process. But this is the price to pay, I would say, to be able to process data of different sensors, which can really make the difference if your application is time sensitive. So if you're working on Sentinel and you have a flood and you need to wait for 2 weeks for the next image, and maybe the next image is cloudy and you need to wait 2 more weeks, and then you have to wait a month. I mean, you cannot do rapid intervention in that case. But if you have 2 sensors imaging the same place, a few hours difference, even if they have different bands, you can still align and have a detection. And I think that this is like the strong power of methods like that. And here there was another example of Landsat 5 versus Landsat 8, where also there were a couple of months difference between the 2 acquisitions. So I mean, the detection problem becomes even harder. Okay, but as before, I've shown you a study without deep learning, and now I will go deep learning again, so that we can have a bit of like the pre-deep learning era and the after deep learning era. And this is a study that we had last year with a student of mine, Marit Lenstra, in the Netherlands, my former university, and we tried to apply a logic that was similar. So we wanted to find a data representation, so it's a projection again, if you want, that will like uniformize unchanged areas, and so by doing that, it will make like change standard. But in this case, as before, I mean, we have 0 labels. So what can we do if we do not have labels? Well, we can use some very recent and exciting methods coming from the self-supervised family. And self-supervised learning is a paradigm that is getting a lot of traction now. So, I mean, if you're starting now, that's probably a universe you would like to have a look at. And it's basically a set of methodology that will learn from what we call a pretext task. So it's not the task you're trying to solve itself, but it's a task close enough that will teach you something useful for your problem. Okay? So, for example, in our case, we want to learn change detection at the end, but we don't have labels. So we will try to learn an auxiliary task that is to make the data spaces less dependent on atmosphere, illumination, and seasonality. And we can learn from that if we can invent a task for which we can get the labels for free. And I will show you in a second how we do it. So here you have really a sketch of what I just said. Sorry, I should have passed the slide before. But basically, you have a data set for which you have no labels, and you will train a model using this pretext task for which you can have the labels for free. And when you have learned this will already, it's kind of a warm start of your model. But so your model will be already half trained so that you can take the little labels that you have for the task you're trying to solve and just fine tune it to be very efficient on the final task. See it as some kind of pre-training that is made in an unsupervised way and that can really help you solve your final problem. In opposition to a pre-training that is done on ImageNet, on another type of images of ground versus satellite, looking cats and dogs, and something that is quite irrelevant for your final task. So what are these pretext tasks? In computer vision, people have been very creative. So they've been trying, for example, we're doing object detection to try to understand part position modeling. So they were taking an image, like this cute image of a cat here, and given a patch and another patch, try to predict what is the relative position. So if you have the head of the cat and the right ear, or I mean left ear for the cat, then the response will be 3, because this patch with respect to this one is at position 3. And by doing that, we'll learn how objects are decomposed into parts, and then the ears are on top of the face, and then the face is in the middle, and things like that. In other papers, they were interested in models that would be rotational invariants. So they were basically generating their labels for free by rotating the image. So they were taking the image, rotated by 90 degrees, and then try to predict 90, which is the degree that was applied of the rotation. And by doing so, they were forcing the model to learn that the image was actually rotated and that this was not important. And by doing that, a model trained like this is then more efficient to solve problems where the image that come in can be arbitrarily rotated. And of course, I mean, this is useful, for example, for us in remote sensing, because in our case, I mean, a car, if it's like this or like this or like this, it's always a car. Okay, let's go back to change detection now. So how can we do that for our own problem? Because this is the thing we are interested in. So remember, we want to warm start the CNN to do change detection, and we don't have labels for that. And most importantly, we want to discard all illuminational, seasonal changes, because these are not the changes we are interested in. So we want basically a pretext task that will tell us if a change that I'm seeing is due to a real change or just to some artifacts effects. And what I want is basically that the features I extract from image become independent from these artifacts. And in order to do that, we used a strategy that is similar to the one of Dersh, which is, if I can come back, similar to this strategy here of the cute little cat. So we're not trying to predict relative position, but we were trying to predict across two images if the patch we were observing was of the same place or not. Okay, I know it sounds stupid as a task, but if you see in this example, so when we were comparing the red patch to the green patch, the answer would be 0 because it is the same location. It also means that if the model wants to predict some change, it shouldn't, because we know that this dataset is completely unchanged, even though we don't have labels. But if we then sample a patch here, like the red one, and the blue one here there has been a change. But this change is due to the fact that the area is not the same, so we're sure that there is a change. So you see, we are generating labels for free simply by sampling patches from the image. And we know that there is no change if they're sampled in the same place, and that there will be a change if they're sampled in different places. Of course, we are not solving the change detection problem in the end, because this task is way too simple. But we are already teaching the model that the illumination difference it will observe will only due to illumination and not to an actual change. Then we can do, this criteria even a little bit more fancy, and we could say, okay, instead of doing it by pairs as a classification problem, we will look at the features themselves, and we will try to make the features of patches sampled in the same place as close as possible, and to make them as different as possible from features of patches sampled in another location of the image. So this is like contrastive learning, it's called, and it basically teaches the model to project in the same place the patches that will correspond to the same location, while you will try to keep as far as possible in the feature space the feature extracted from patches of another location of change if the change happens in the image at some point. But whatever the pretext task that you use, the idea is to really take the two images, like here, image 1 and image 2, extract some patches, and from these patches, learn a neural network that will predict one of these two pretext tasks. So is it the same place or not, or simply trying to squeeze similar patches together and push away different patches. To learn this guy, we basically sampled Sentinel-2 images from all over the world. So here, every dot is a major city in the world, and we sampled one Sentinel image centered at the geographical center of the city. So for each one of these images, we had it all, and we started to sample patches, and this is completely unsupervised. We didn't have any labels about change. The only information we were using was the relative position, and with this position, we could basically extract all our labels for free. By the way, this dataset is available and open on Zenodo, so if you follow this link here, you can get to the data set, or you can also find it in the paper we published in ICPR this year. Once you have learned this representation that will in the end describe your image, so you will have here a yellow box, which is a CNN that is able to tell me, like, to group features together for patches on the same place where no change has occurred, and push away features where you're sure that there are changes. We can take these features and put them in a second model, and this model will take 2 images, and but this time it will classify change itself at the pixel level. But it is possible, like this, to like use all this knowledge you learned before about, you know, illumination, atmosphere, and variance, and like plug it by default in the change detector, which will make the work of the change detector much easier, to the level that you could very well use the CVA, so without any labels and any learning, or you could learn a very simple model like a one-layer convolution neural network or an MLP if you want. And by doing so, you see that you use the knowledge you have generated in an unsupervised way and basically plug it in your change detection algorithm, for which you have a handful of labels. And of course, like learning the whole model from zero will be not possible, but with the self-supervised part, we're basically able to give it a head start, and the model can do well. So for the second part, we use a dataset that was disclosed by Dot and colleagues. So again, Dot and colleagues, and it's called the OSCD dataset, which is also totally available on the DASE website of GRSS. And you know, it's a collection of 24 pairs of Sentinel-2 images that you can see here, and it comes with labels this time. So we basically use part of the labels that we have to train a change detection model with these features we learned in the self-supervised way. And the results you will see in the next slide are basically obtained after uploading our results on the DAISY server. Now, just disclaimer, we are not winning the DAISY leaderboard, but that's obvious because we are going after methods that were trained and tested with all the labels available for this task, while we are not. So how does it look like? So we have a big table with a lot of numbers. Don't start to look for the number themselves. I walk you through it. The thing that you need to look is that on the top half here, it's all the methods that are self-supervised, either using task 1, so predicting if it's the same place or not, or task 2, so this push and pull self-supervised method. At the bottom, you have some of the models that are from the literature that come from these 2 papers, still by Dot and colleagues. So the first thing that you can see is that the precision is pretty low, but it's low all the time. Like if you look at the early methods, like fully supervised, it was also the same case. And this is because our task 1 is way too simple, like predicting if 2 patches are collocated doesn't give us enough information to really like make the difference between atmospheric effects or illumination effects. And this leads to a lot of false positives. So you can see that recall is very high here, like specificity, but the recall is very high because you're predicting change all over the place. But it's the same problem that the original methods had, which is funny because, you know, if you look only at accuracy of the methods, you have good numbers, but like if you start to look at the maps and do things like that, then you see that sometimes the story is not so pretty. But task 2 seems to work a little bit better, and we have a precision that is double as high. But this time we also have high recall, and we get to F1 score of 45%, which is not bad if you think you are just using an unsupervised pre-training plus just a few labels for the task. And you know, we are getting closer to, you know, more complex fully supervised methods that of course are doing better than us, but this is not the point today. But I mean, I hope that this show you that using these self-supervised approaches can help you train models that you could not train otherwise, and that it's mostly a matter of imagining a good pretext task that makes sense for your problem in remote sensing, And this also helped us a little bit exiting this, this like story of always looking at computer vision papers and trying to apply them as they are, but mostly at thinking about, hey, what is specific to my remote sensing data, and what can I really design to solve for these specificities. Okay, I promised Jefferson I will talk 45 minutes, and it seems that I'm exactly at 45 minutes, which means that I can take a couple more to be a bit too long than necessary. Just to conclude, so I hope you've appreciated this tour of change detection, going from more traditional methods to very, very exciting deep learning algorithms that are now being used. But I also hope that you have seen that this is not a simple problem. And just don't believe papers that tell you that they do change detection at 99% accuracy. They're just using the wrong metric. And change detection is hard, especially if you do it right, which means detecting changes in different geographies, with few labels, and with all kinds of perturbing factors. Now, we have more data, and nothing is deployment ready yet, but we are getting there. And I think there is a lot of very, very exciting research to be done. So please jump on the wagon of self-supervised learning or unsupervised learning, or the wagon that you like, but do it well, and keep in mind that remote sensing is, it has a lot of very interesting and unique features that you really should encode in your methods. So thank you very much. I would like to thank all my collaborators at ECO. This is my team, and they are great, all of them. And also, if I can do a very last second advertisement, I just wanted to tell you that we have our book that is just published a couple of weeks ago, Deep Learning for the Earth Sciences. And then you will have a lot of inspiration of everything that is going on in deep learning for many, many fields of earth science and remote sensing. There is a paper that I'm very, very proud of, where we sketch future ideas and very exciting avenues to study for the future of Earth observation and machine learning AI. And what they presented today is, of course, part of it. And finally, for those who are undergrads and would like to, enter the adventure of a PhD, let me also advertise that the Ellis PhD call for 2021 is actually open. And Ellis is a pan-European network of laboratories in machine learning. And if you apply to Ellis, basically, you get access to all these labs, and all these labs will get your CV. And you never know in which lab you will end up to, but there are some pretty awesome labs there, and including a number of people active in machine learning for Earth and climate science, which are very, very happy to read through your CVs, and who knows, maybe starting an adventure together. And with this, Jefferson, I think I'll stop. And I'll also stop sharing my screen so I can see you. And we can start the discussion.
Thank you very much.
If you're there.
Devis, it was a very nice presentation. And
or excellence.
Yeah, so we can now start our question and answer session. And for this, I would like to invite Dr. Gilson Costa.
Wait, I can hear you very well, Jefferson.
Oh, okay. It's okay at this moment. Maybe I'm having some problem with my connection. Can you hear me?
Yeah. It's okay
Devis?
for me.
Hello.
Hello, David.
I don't hear anybody.
Yeah, at the moment I can hear you. Maybe we have some problem, but I believe it's your connection, because Gilson is hurting me. Okay.
It's okay here. And now his screen.
Unfortunately, I really cannot hear you. What I can do is that I can maybe go through the question myself.
Can you hear me now? No.
Okay, I believe Davis are going to connect. So I may I will have this opportunity to invite Mateus Barros, which is a young professional representer here. He's a student, a PhD student from University of Minas Gerais. And I believe Tuia is going to reconnect at this moment. So we have here a lot of questions, actually. And as far as Dave is reconnected, we can start. Okay. At this moment, we have almost 60 attendees in our webinar. It was a very great number of people. I believe it's very nice to have you here. And we have a lot of questions, I believe, here. So let's check it out. Devis, can you hear us?
I think he's having problems.
Okay.
Well,
let's wait a little bit.
WhatsApp is working. I think Facebook too. So okay, good.
Sorry, it took a second to reconnect.
No problem. Can you hear us at this moment?
Yes. It was completely, like blocked before, but I'm back.
No problem. We have almost 60 attendees at this moment. I believe it's a good audience. We have people from many countries and also many cities in Brazil. So it's a pleasure to have you here once again. And we may start. I will ask for Gilson if he have some question. Gilson, we can start the discussion like this.
Okay. Thank you very much, Devis. Very interesting talk. We have been dwelling with change detection for a while here. I mean, I and my group especially, we are working on deforestation detection in the Amazon and other biomes and stuff like that. We are using deep learning, and one problem that we have is about the generalization of the methods. So, I mean, we're detecting change in the Amazon in different regions. And when we apply a classifier that has been trained on a region to another region, even in similar regions, not so different, there's a important drop in performance. So we're trying to work with domain adaptation architectures or approaches, but I would like to hear from you. What do you think about this problem of generalization in change detection and how we can approach it? I know it's a big
it's a big question.
Yeah.
Yeah, I mean, I think generalization is the biggest problem we have in all these studies that we do. And I think, I mean, it's very brave to attack it, because it could be, it's always maybe a bit easier to stay into benchmarks and not be brave enough to go out of distribution and see how it works. I personally think that these approaches based on self-supervised learning are a good step in the direction of generalization, because they really allow you to learn from very large amount of data without requiring the labels. So it really permits you to cover much ground with respect to different spectral and optical situation that you could observe in the images, but you never observe them in training because you don't have the labels. So this is one. Other than that, Yeah, I mean, you mentioned domain adaptation, and that's definitely the way to go. And I mean, for example, a very big fan of continual learning. So try to have models that keep growing, including more information without forgetting what was before. Because as long as we keep fine-tuning models to a new region, we will only be good in the new region, and
Yeah.
we will lose everything in the previous. And it's so I think that all these concepts of self-supervision, continual learning, and domain adaptation is really the way to go. But their combination is not clear at all yet. So it's
Okay.
yeah, it's
Yeah.
very super interesting
I
topic.
know. I mean, it's just a provocation because this is a problem. This is an important problem. Well, in general, not only for change detection. If I may, I just wanted to make another quick question. Years ago, a decade ago, we were working. All of us were working a lot with object-based image analysis. And well, there's this interesting thing about object-based image analysis that would maybe prevent some errors related to registrations of the images and stuff like that. We threw that all in the trash. I mean, people are not working with that anymore. What do you think about that?
Oh my, I'm not making friends today, I think, with this with these questions. No, so object detection, I mean, the object-based image analysis is what you're talking about. It's it's a paradigm that had a lot of traction a few years back. I mean, it still does. Not everybody needs to go deep learning. Like
Uh-huh.
let's be clear. But I've seen. I mean, there is a lot of research. Now, for example, with graph neural networks, that can use objects that are not pixels array as a base learning element. So it's definitely possible to use objects detected by an by an OBIA type of algorithm and then encode them into a kind of a deep learning framework. It is possible. I mean, there is nothing that prevents it. It's just, even more complicated type of approaches. So I don't know if it's worth the effort. I mean,
Yeah.
this is to be studied. Yeah.
Okay. Wow. Okay, thank you very much. I mean, there are many other questions, so I'll.
Yeah. No, but for example, we had this paper out a couple of years ago where we were like using both approaches together. So we had a pixel-based deep learning algorithm running to make like characterization of land cover, and on the side we had an OBIA type of algorithm making a hierarchical segmentation of the image, and then we were trying to connect the two with a kind of an energy minimization framework. So also, not everything needs to be learned end to end. Like you can
Yeah.
learn parts of it in a way, parts in the deep learning, and then try to combine them afterward with some, like energy minimization. In the end, it's including prior knowledge, and if you have priors about objects, this will help a lot. So I don't know, food for thoughts, but
Okay, thank you.
thank you.
So, so I believe we can pass to the audience. We have a lot of questions here. Matheus, can you read this question, please?
Yes, the first question from Hugo Neves. How do your team deal with the inherent label imbalance in self-supervised learning for large-scale remote sense applications with non-RGB bands or even radar components?
Wow, that's a very intricate question. Okay, labeling balance that we control in these experiments by sampling, like controlling the sampling of the collocated versus non-collocated samples. Because like we were using, for example, a cross-entropy loss for the prediction whether they were collocated or not. And so we tried to keep it more or less stable. And if it was unbalanced, we were using weights in the loss function to make sure that one was not like completely buried by the other. Because we wanted the model to see situations that where the patches were collocated versus non-collocated. And the non-collocated you can have much more than the collocated ones if you do like the full combinatorial. So it was kind of a controlled environment. And the second part is non-RGB bands or even radar components. So in the study I presented, we were working with Sentinel, and we had non-RGB images. And this is also, one point in favor of using the self-supervised approaches, is that pre-trained models that are non-RGB are pretty hard to find. So if you need to learn from scratch, you need to be able to learn from scratch. So using a strategy like the self-supervised learning allows you to have 1 million labels without having to label a single scene. And then it allows you to, like, warm stars model that will accept 10, 12 dimensional inputs as such. So that's probably one advantage of using this type of strategy. And also, I must say that, pre-trained models for Sentinel type of images are starting to pop, and then it could be possible to now use those ones. Even radar components, that's also tough. You can always apply deep learning models on radar images, assuming that there are images, which is completely wrong. I've seen a lot of that for denoising, and that's pretty neat. Now, there is a whole movement of developing deep learning algorithms specifically for SAR that will, take into account all the things that happen in SAR. I'm not an expert, to be fully honest, so I don't want to say stupid things, but layover, things like that. And look, for example, at a tutorial given by Ronnie Hench. It was given at the Uyghur Summer School recently, and he's been talking about that. And it's on YouTube, so you can find it easily. So I hope I answered all the questions.
Okay, thank you. This guy is a questioner. We have a lot of questions from him. I will just show another one. Most of the state-of-the-art algorithms, for example, CLR, MoCo, SWAV, SimCian, are only equipped to deal with RGB images in balanced scenarios as ImageNet, but struggle with label imbalance. It's a complement of the
yeah. What you say is true, and yeah, I mean, in a way, there is quite some research about how to deal with class imbalance. So you can think of, the focal loss or all these other papers that are really studying. I don't have the names of the exact losses, but there is quite a few. There are people who try to first learn balance and then learn imbalanced. There will be a kind of what's it called? Continuum learning, no, universal learning. I don't remember the exact name of that.
Contrastive learning, maybe.
So contrastive learning is a way of learning in a self-supervised way. Like MoCo, for example, in this list, is typically a contrastive learning type of algorithm. But the loss you put in, you can make it like aware of class imbalance. So this could be a way to not struggle anymore with class imbalance, but I mean, it needs to be studied. It's true that the benchmarks, like ImageNet, it's balanced. So
yeah,
I mean, you need to start somewhere. I think it's
quite
good.
easy. We have more questions from the audience. Can you read that, Gilson, please?
You showed an application of self-supervised approaches for patch classification. Could you please discuss the possibilities of this kind of approach to semantic segmentation?
To semantic segmentation. Okay, let's see. The thing that I showed here basically learns an encoder that is good at discounting for atmospheric effects or illumination effects. So it's an encoder, if you want, that is not too much bothered at whether you took your image in the morning or in the afternoon. Now, you can take this encoder as it is and plug it into a semantic segmentation model that does semantic segmentation. So, meaning that afterwards as a decoder that does semantic segmentation. So it's something that people do. And so really, the story of self-supervised learning is to give you features that answer to a problem that is not the final one you're trying to solve. So it's a perfect application of this. You learn your encoder to discount for atmospheric effects, but then your final task is not dehazing. Your final task will be semantic segmentation.
Yeah.
So I think that it's almost possible out of the box. But by the way, I didn't show the maps, but stupid. I mean, our application is semantic segmentation. Like it's a semantic segmentation, change, no change. So we have two classes.
But then you do it through patch-wise classification, or you do a
So the
dense.
self-supervised part is patch-wise, but the
Okay.
second task is at the pixel level.
So you just plug in a classifier that is a decoder.
Yeah.
Okay.
Yeah, you need to have a decoder then that will map to every single pixel.
Okay.
Yeah. Thank you,
Okay.
Jose.
And have you tried, skip connections between those components or not?
Not here. No, we were trying to keep it very, very simple.
Okay.
Just to understand if it was worth it. And I mean, you can complexify it.
Yeah, all right.
As you wish. You know?
Okay.
Okay, so let's come back to our team here. Mateus, have you some questions for Devis?
Yes, initially I had a question that was pretty much exactly the one that Gilson made, but there's another one that is not about generalization like for different places, more about using different data. For example, when you're using that discriminating overlapping patches strategy that you showed us, how do you think it should be the best way to deal when we are using different types of data? Like instead of using Sentinel in two different times, we are using two different sensors. Maybe they're not aligned, or maybe there is some kind of difference between them in terms of data. What do you think would be the best approach to deal with this?
That's actually an interesting question, because it enters all these like multimodal type of approaches that I like a lot. So I think the simplest way to go with it would be to basically having a structure where you have your two images. So they need to be collocated. Otherwise, I mean, you need to have something. So collocation is usually a good thing to start with. And so you have your two patches. They correspond to the same region. Maybe not at the exact pixel level, because they might have different resolution, whatever. And then you have your two encoders, everyone giving you a feature representation specific to that image. And if you do your design well, you can make it in a way that your two representation can then be aligned afterwards. So you will have just to have an extra step of learning to get to the common representation. And once you have this common representation, you can then learn it with your final pretext task. Now, this works for the pretext task, which is at patch level. When you then move the encoder to the other side that does change detection, you need to have more or less the same type of constraint. So maybe you want to move the two encoders rather than the fusion part, because you will need them to process the different data. So I mean, it's really a question of design that is super important. Yeah.
So we have more questions from the audience. Hi, I am Shueri from Wageningen University. Curious about how I create the best deep learning algorithms for change detection can be.
This is a tough. Hello, Shurui from Wageningen. So we're from the same university almost. How accurate? That's a difficult question. It changes, it evolves a lot, and it depends on the problem you're looking at. So in these benchmarks I showed in the presentation, we're roughly 30-40% accurate. If you really like take into account an F1 score that will take only the change class into account. And if I guess in the problem of deforestation, it must be probably lower. But I don't know. It's so problem specific. So the the task I showed in the talk are very, very high resolution. So like every error counts and your number goes down very quickly. If you detect a building and the true building is just displaced a few pixels, you're still doing a lot of errors. So my guess would be a lower resolution numbers should be higher, and a higher resolution they must be lower. But it's speculation. I cannot really tell.
Yeah. Yeah, well, I think it's interesting that, you said that maybe in the first station detection, the accuracy might be very high. Indeed, in some areas, it's higher than in the others. But an interesting thing is that, well, deforestation is not a simple thing. Like, I mean, there are different practices of deforestation, I mean, it's not only the absence of trees and stuff like that. It's also has to do with the process. So you have to take into account, well, some sort of behavior, not, human behavior. And not only like the plants and stuff like that. So this is another dimension for the problem,
Absolutely. No, but Jason, don't get me wrong. I say that I thought it would be more difficult in deforestation,
Okay.
not easier. I say that the accuracy should be lower. So I think we are on the same page, and we definitely need to talk about it offline, you and me, when
All
this
right.
is.
We'll do that.
Cool.
Mateus, can you read that one?
Yes, Guilherme asked, what about methods based on generative models such as GANs and cycle GANs?
Okay, I think I've seen that a little bit in the literature, like people using a GAN to take an image and to make it look like the image at the other time. So I think I've seen some papers trying to do that. It is technically possible. Like look, for example, at the works of Onur Tasar from INRIA. He has been working a lot on GANs type of methods to make images look more similar. Then he was not working on change detection itself, but he was working on blank cover classification, and he showed that with a GAN you can reduce this illumination or color differences that will make it easier to generalize across places, which is very similar to what we are discussing here today. So check it out.
Yep. The problem is that GAN is very difficult to reproduce the spatial relationship among the objects in the scene.
Yeah, it actually creates a ton of artifacts. And especially if you want to do change detection, you don't want to create artifacts by the GAN generation process.
Yeah, like this.
It's always a bit tricky to work with GAN, but there are people who have been doing like very, very nice works. For example, Onur, I mean, if I go back to him again, he was really like trying to modify only the spectral values and not modifying at all the spatial component, which will make that you don't, they was just modifying the histogram with the GAN, which basically makes that you don't have spatial artifacts in the images and just the color gets changed. And I think it was a very interesting way of approaching that.
Yeah. We have just only 2 more questions and we can finish the session. Okay, Devis?
Okay.
It's okay for you?
Shoot.
So one more question from Hugo Neves. I believe it's a very good question. Gilson, can you read for us?
Is there any development in using out-of-distribution recognition to perform change detection in an unsupervised manner? Maybe pairing it with some metric learning model?
Well, I mean, it's a little bit what I presented, no? We use the word to learn a representation with a metric that was dependent on a pretext task, and then we try to use it for change detection. No, of course, jokes apart, I mean, it was not tackling the out-of-distribution problem directly, but it was more the other way around. Like, let's try to learn the representation from images from all over the globe, hoping that the representation that we learned can be ported easily. But Hugo, everything you say makes sense. So I'm sorry, I'm always giving you the same answer, but give it a try.
So the last question. Mateus, can you read for us, please?
Do you think we can apply change detection to update cartography databases?
I think this is a good deal of why we're doing change detection. So, there is all the disaster response, monitoring, deforestation, for example, angles, but a big part of change detection is about updating maps. And I'm sure if you look, for example, at the works of the group of Clément Mallet at IGN, so the National Mapping Institutes in France, that's exactly what they're doing. So they're using change detection technology to make the update from one date to the other. So definitely recommended reads the works from the group. I'm also starting a project here at TCO with our Swiss cartographic office to go in that direction. So that very good remark, and the answer is an absolute yes.
Davis, I thought you that was the last question, but we have once more question at the moment. Can you have a last one? I promise you.
The coffee
Okay.
will be bigger afterwards.
Please, Gilson, can you read for us?
The self-supervised approach considered images from all over the world to aid spatial generalization. Could it also consider images from different years to help temporal generalization?
I think we will need a very long time series for that. And so the current data set, it's bitemporal. So for every place, we have 2 images from Sentinel in time, because we want to learn this pretext task by comparing patches across time. Now, if we had a very long time series, we could maybe learn something about this, but I mean, it should be necessary. And it could be seen here as a way of like increasing your bag of positive examples, like collocated patches. You could say, okay, I mean, now I have 2, but I could have 10. And for all this, my labels would be the same. Or you could be after some things that happen at a certain moment in time. But this is a completely different problem, and I don't think it's like change detection itself. It's more like historical monitoring, trying to extract trends or things like that. But in any case, as for all your very relevant questions, like the answer is yes. Try it out.
Okay.
So I believe we can finish our webinar. I would like to thank you, Davis, for this very nice presentation, also for the very nice answers you have done for our audience and also for our invited researchers. I would like also to thank Gilson Costa for being here virtually in our webinar, and also Mateus. So thank you very much. Thank you, our audience. And if you have more questions, we can contact our organization, and we can help you to contact Davis. Davis is a very good researcher. I believe he is looking for good students all the time. So it's as well as our webinar is for students. So I believe it's a very good opportunity to say that. So thank you very much, Davis. Do you want to say something to finish our webinar?
I think I can mirror what you say. Thank you very much to everybody to be here. Maybe it's the middle of the night for you, so I really appreciate. And Jefferson, Gilson, Mateus, thank you so much for the warm welcome. And just drop me a line if you have more questions. Everybody else in the office, I'll try to answer as fast as possible. And yeah, keep doing good research. I think that's the most important thing.
Okay. Thank you very much, man.
Thank you, Davis.
Thank you, guys. So I will going to end the broadcast. You can keep here to last words. So in the background, okay. So bye bye, people. Bye bye, audience. So to the next webinar. See you.